So this is like take 3. This is a video to support the inductance labs for the theory portion of our course. So I'm going to show you how by changing the amount of inductance in a circuit, we're able to manipulate the amount of current that's flowing in the circuit, okay? So my last attempt, I used a multimeter that a student had blown the fuse in and my circuit didn't work. So I have verified that I have an ammeter with a functioning fuse. So that's a good start. So here I have a coil of wire. Okay, so ultimately a coil of wire is an inductor, a very elementary type coil inductor, but it is essentially a coil of wire, which is an inductor. I did a resistance reading across the coil and I read a resistance of 1.9 ohms. Okay, so on the board here, you can see that I put that value in using an Ohm's law formula to get an expected amount of current draw once I energize that coil of wire, okay? 120 volts is what is sourced on our bench, okay? 1.9 ohms, which was read across the coil of wire with my multimeter. And I'm getting an expected draw of current of 63 amps. So just a reminder, our fuses our benches are fused at 12 amps. So when I turn on that coil of wire, I'm expecting that fuse to open. Okay, so let's energize the coil of wire and see what happens. Okay, so you can hear the coil actually humming, which is a very typical sound in an electrical place of distribution, right? The sound of humming. A lot of times that's an indicator of a coil generation voltage, right? So our expected current was 63 amps, but you can see here on the multimeter, I'm only reading 8.2 amps. The reason that I am only reading 8.2 amps is because this is a coil of wire and it's opposing that build of current simply by producing a counter EMF in our turns. That's opposing that rising current from our expected 63 amps to our 8.2, okay? So I wanna just show you how we're able to change the inductance and then overall show you how that changes our current. So if you can see on the board here, I have our formula for inductance, okay? So L, inductance, equals number of turns times permeability times area divided by the linkage path, okay? So I'm going to manipulate some of these variables, and on our meter, we're going to be able to see how that's affecting the overall current. Okay, so number of turns of the wire, I'm not physically able to remove any of the turns or physically add any of the turns, but I am able to change the permeability of the core as well as the area of the core. So when I initially energized this coil of wire with our 8.2 amps generated, I was essentially using a coil with an air core, right? So I can change that core by inserting these iron cores and thus changing the amount of inductance that's created in our circuit. And then with changing of the inductance value, we're affecting the overall current, okay? So, and I will look at that in regards to our formulas. So permeability is the ability of our coil to generate lines of flux, and that's changed by the type of core we have. Area of the core is also affecting and directly proportional to the amount of inductance that's being produced in our coil of wire here. So I'm going to go from an air core to an iron core, okay? And we're going to see how that affects the current. So if I am replacing the air core with an iron core, I am increasing the permeability of the coil, and directly proportional as it is laid out mathematically in our formula, we would expect an increase in our inductance. So that comes back to our inductive reactance formula, because inductance itself is not the variable that opposes current flow. It is the inductive reactance as a component of impedance. So XL equals 2 pi FL. So when I increase the permeability of my inductor, I'm increasing the inductance. If I increase the inductance, because XL, inductive reactance, is 2 times pi times frequency times inductance in Henry. So if I'm increasing the inductance, I'm increasing the inductive reactance. In AC, we no longer just use resistance as our variable of opposition, we use impedance. I equals E over Z. Because this is a pure inductor, meaning minimal to negligible resistance, my impedance will equal my XL. So if my XL goes up, current is expected to go down. Okay? So by me changing the parameters of my inductance formula, I'm directly impacting the inductive reactance, which is inversely impacting my current, okay? So now I'm replacing the core. So we had 8.2 amps on the coil of wire with an air core. So now I have an iron core. I turn on my circuit. Noticeably, my humming has decreased, which is an indicator of more efficiency, okay? And my current is now at 4.5 amps, okay? So we can directly see how manipulating these components of our formula is effectively influencing our current, okay? So by me changing the permeability or the area, because essentially going from an air core to an iron core has increased the area of the core, my inductance went up, my inductance went up, my inductive reactance went up. If my inductive reactance goes up, my current goes down. I'm creating a more efficient inductor, okay? So again, I want to really hone into the fact that I can manipulate the amount of inductance by changing the variables within the formula, okay? So now I have, and I just want to note that the metal itself now is hot. And the reason it's hot is because it's a solid piece and I am experiencing eddy currents, okay? So those are the circulating current losses or currents that are producing loss within our cores, okay? And we would laminate our cores to eliminate those eddy currents, okay? So now I'm gonna replace that core with a larger area core, okay? So what's gonna happen? My area goes up, my inductance goes up, okay? If my inductance goes up, my inductive reactance goes up. These are all directly proportional. XL goes up, current goes down, okay? So when we had this core in, we were drawing 4.5 amps. Now I've increased the core with a larger area core, and let's see what happens to our current. Okay, so now that I've replaced this core with a larger area core, my current is affected proportionally to that. So right now, this coil of wire is drawing 3.39 amps, okay? So hopefully this little demonstration helps you realize how we are affecting the overall current by adding inductance into a circuit.